So thank you very much for these introductions, Nick. And I also want to thank the IEEE for hosting me, and also the Robinson Research Institute. This is my first trip to New Zealand, and already it's become special. I'm really thankful of the good welcome I've been getting here. Today I'm going to talk about compact fusion in general, and since there's a mixed audience, and most people don't have knowledge of fusion, and some may not have knowledge of superconductivity, I'm going to do a very short background on superconductivity, and the people here who are superconducting experts will go, this is too simple for me. So I just want to get some basic concepts across, because it's necessary to understand superconductivity in the sense that we would need them as large magnets for magnetic confinement fusion. Then I will go into the basics of magnetic confinement fusion so you understand what goes on in a fusion reactor, why we're interested in it, and then describe the state-of-the-art of fusion magnets and the biggest international research project, that's a scientific research project that's going on right now, the ITER project. And then the exciting part are the new developments in magnet technology that are coming, we believe, because of the advances that have been made in high temperature superconductivity. But before I start, a word from my sponsors, which is the IEEE Council on Superconductivity. It's a part of the IEEE, and we promote programs and activities that cover the science and technology of superconductors and their applications. So it's very broad, all aspects from electronics to large scale to materials. The Council's member societies include all of these because it's a very interdisciplinary type field, and I want to note too that power and energy is clearly a part of it, but you can see how it extends over all types of electrical and electronic engineering applications. And for the students in the crowd and the senior researchers here, the Council does give out IEEE awards and recognition. I'm chairman of that committee, so I'm trying to encourage people to apply or submit. So they're career awards. There are, for the students, graduate study fellowships. They are competitive, but several are given out every year. And then there's also awards for best contributed papers published in the IEEE Transactions on Superconductivity. Okay, so superconductivity. Most of you know that superconductivity was discovered by Kamerlingh Onnes way back in 1911. It was sort of a fluke that he discovered it, but the basis for him discovering it was in 1908, he was the first person in the world to liquefy helium. At that time, around the turn of the century, there was a huge race on among the physics labs in Europe to see who could liquefy all the gases down to all the way down to helium, finally. And helium was the last one held out. He had a big competition with Sir James Dewar, who you may know who the Dewar is named after. But he did it in 1908. And of course, you could see there's only very small traces of helium they could collect in those times. It was very difficult, and it made it very difficult to do low temperature experiments. But here's a page from his notebook where you see he was measuring the resistivity of mercury at very low fields, and all of a sudden around 4.2 Kelvin, it just disappeared. It says 10 to the minus 5th ohms, but that's as accurate as he can measure resistivity in that time. And he wrote in his notebook and called it superconductivity. So superconductors act different than normal metals. Normal metals, and especially good conductors, their resistivity decreases with temperature, and then at some very low temperature, there is some residual resistivity once most of the photon activity is finished. Semiconductors have an increasing resistance with temperature, lower temperature, but superconductors come down resistivity as if it was a normal metal, but at some point it goes through a phase transition and becomes superconducting. At that time, it's because of, this is sort of a phenomenological model, and this is the whole theory of superconductivity that people have won Nobel awards for. But basically, the electrons condense into a superconducting state into what are called Cooper pairs, named after Cooper, who was one of the Nobel laureates for the discovery. And they are allowed to move through the lattice, exchanging phonons back and forth with the lattice, but in a non-dissipative way. And so they become what people have called perfect superconductors. However, perfect superconductivity is not actually the main feature of superconductors. It's the one we use for applications. But what you really have to understand is that the superconductor is diamagnetic. So you've probably seen this effect in science labs and so on, where you can levitate a magnet over a superconducting device, and that's because of the repulsion between them and the induced currents. So what happens if you were to take a superconductor and it's above its transition temperature and you put it in a magnetic field, there would be no effect on the field or on the material. It would just pass through, it wouldn't know it was there. However, if you now cool that down in a magnetic field, it would expel it. So the real feature is that the superconductor does not want flux inside of it. It wants to expel all flux. Now, this is a perfectly diamagnetic material that was first discovered. And so when Camerlingonis tried to make a wire out of it to do things that we want to do with coils and windings, he discovered that as soon as he started putting current into it, the superconductivity disappeared. And that's because the ones he were using were type 1 perfect superconductors, and they expelled the flux. So when he put current in it, the local field made by the wire itself was enough to kill the superconductivity. However, there are what are called type 2 superconductors now, which allow some partial flux penetration. It's a very complex materials problem of how to develop materials that can allow a lot of flux penetration while carrying a lot of current. But in general, you would see a superconductor, for example, embedded in some copper wire for both thermal and electromagnetic stability. And at some point, it would all stay in the wire because the resistivity is zero, until you had some type of a disturbance. And it could be a temperature disturbance, it could be a local magnetic field disturbance. But if the disturbance is big enough to destroy the superconductivity, then the current wants to shift into the low resistivity thermal copper path. Of course, there's Joule heating going on, and you need to cool it from that. And so in this indicates there's some helium around it. This is the way early magnets were made. And if you could transfer the heat to the helium faster than it was generated from the Joule heating, then the superconductor would recover. If not, the temperature locally would get hotter and hotter and propagate the quench, and that the normal zone, and that's called a quench because this has the effect of boiling off all your helium suddenly. So there's a lot of electrothermal stability that characterizes the design of a magnet because you have to take that into effect. The other thing for the electrical engineers, this is only for the electrical engineers, these materials are partially diamagnetic. The reason I show this is because as you change the field, you can go around a hysteresis loop, which is dissipating energy. So when we say a superconductor is lossless, it's lossless in DC fields under DC conditions. But if anything changes the magnetic field, there will be a dissipation. And that's something that needs to be taken into account when you're using it, trying to use it in a transient or AC application. Now, what really defines the superconductor for practical purposes is the critical surface. So the earliest good superconductors were niobium titanium and niobium-3 tin, and you can see that there's a volume of operating area that's bounded by a critical temperature, a critical magnetic field, and a critical current density. If you're underneath this surface, you're superconducting. If you transit out of this for any reason, field exceeds critical or temperature exceeds critical, so on, then you're in normal region. So the whole trick of designing a magnet or some application with the superconductor is to keep it operating under its critical surface. So these are called low-temperature superconductors. But in 1986, there was discovery of high-temperature superconductors. This happens to be IPCO. I'll talk a lot more about that later. But you can see what's happened here is the critical temperature, the critical field, and the critical current densities are hugely larger than what you have with the low-temperature superconductors. So this gives the magnet designer a huge range for operation and design. The question is, can we actually design and build magnets that take advantage of that feature? There's a lot of information on this slide, but this is back to the discovery of the different superconductors. So it was discovered first in 1908 in mercury, then in lead, so on. Then niobium and niobium alloys are superconducting, and these become good superconductors for carrying current and generating magnetic fields. Then there was niobium-3 tin, which is a brittle compound, and other features like niobium germanium and niobium-3 aluminum. They can be pretty good conductors. There's all types of materials that are superconducting, but not practical for using in any type of application. However, in 1986, Bednorz and Mueller, working at the IBM labs in Zurich, discovered superconductivity in lanthanum barium copper oxide, and shortly thereafter, Paul Chu at University of Houston discovered superconductivity in IPCO, yttrium barium copper oxide. What's really interesting about this is to keep these superconductors cold, you need to operate them in liquid helium, which is 4.2 Kelvin above absolute zero. However, you can see that IPCO and then later the bismuth-based superconductors, there's a couple of versions of that, and even mercury, they have critical temperatures that are above that of liquid nitrogen. And that became very exciting because working with liquid nitrogen is a lot easier than working with liquid helium. And people thought this was going to open up a huge path to power applications, for example. And it did for a while, but it turns out that these things are really hard to work with in some ways, and you have to know a lot about their behavior in order to build something practical. So this is sort of these common ones that are actually used, can be used for applications. And you can see that niobium titanium has a critical temperature of about 10 Kelvin and a critical field around 10 Tesla at 4.2 K. Niobium tin is about double that, 18 degrees and 24 K. So niobium titanium is used for what we call low field magnets, which is maybe up to 10 Tesla. And niobium tin for magnets that you want to use at fields up to over 20 Tesla. And I'm going to show you some examples of that. However, you can see these high temperature superconductors here, and you can see their critical temperatures are 93, 110, 133 Kelvin. And their upper critical fields are huge. You know, these are actually speculation, 150 Tesla, 108 Tesla. You know, this was too high to measure. So now if you're interested in high magnetic field, you can see why people are starting to get interested in these devices. Magnesium diboride is sort of an intermediate one. It's 39 Kelvin and good to about 15 Tesla. So some people are interested in this for applications because it's closer to niobium titanium, and they're hoping it can replace niobium titanium for some of those applications. I mentioned niobium titanium. This is actually the most widely used superconductor in the world, and the biggest market for that is MRI magnets. And if anybody's had an MRI or knows someone who has, when you're lying in the bore of this, you're only a few centimeters away from extremely high magnetic field, about 5 Tesla, and within centimeters of 4 degrees above absolute zero. So you can imagine the cryogenic design of the cryostat to keep that temperature gradient in such a small part is a very difficult engineering problem. The original commercial devices started out at 1.5 Tesla. 3 Tesla is becoming standard, and 7 Tesla is being used for research purposes now. Sales keep growing. Anyway, there's a new magnet has just come online, 11.7 Tesla using titanium, but it cost $140 million, and it took them 10 years to build it. The other big application for titanium that some people have heard about is the Large Hadron Collider at CERN. There's something like 1,200 superconducting dipoles, as shown here. There's a photo in the tunnel, and here's a drawing of what it is, operating around 8 Tesla and about 2 degrees Kelvin. So this is sort of the biggest scientific application of it that's been used so far. Now let's get to fusion, which is the other big application for it. The question is, what is fusion? Well, it's the energy power that powers the universe, our sun, and basically everything you see in the night sky. It's a process of putting light atoms together to form heavier atoms, and then when that happens, if you can get that reaction to happen, forms a new atom and gives off energy. So what's commonly used, or the simplest reaction that people have been trying to use on Earth, is deuterium and tritium. Deuterium is an isotope of water, of hydrogen. Basically, it's a proton and a neutron. And tritium has an extra neutron, so 2 neutrons. If I can put these together at very high energy and get them to combine, they combine into what's called an alpha particle, which is basically just a helium atom, and it gives up a neutron carrying 14 million electron volts of energy. And there's still about 3.5, so about 20% of the energy stays in the alpha particle, 80% goes with the neutron, and this is what we're looking for. You don't normally like neutrons. They could be dangerous, and they do damage to materials and to our bodies. However, they carry a lot of energy, and if you can trap that energy and convert it to heat, and that heat into water to make steam, you can then turn a turbine with it. So that's sort of where we're going with this. The alpha particle still contains some energy, so that you try to keep that recycled within the plasma to give it up before you exhaust it. So where do we get the fuel? Well, deuterium is really abundant in seawater. It's 1 in 6,700 hydrogen atoms. Hydrogen is the most abundant element in the universe. It's over 90% of all matter. Tritium is very hard to come by. It has a very short half-life, and so it's only produced by a few special CANDU reactors and in decaying products from nuclear weapons. So there's very small supplies of tritium. So there would never be enough to run a fusion program if that was all you could do. However, if you have lithium, you can do a tritium-lithium reaction, which I won't go into here, to generate more tritium. And the goal in a fusion reactor is to make the reactor go, is to have that regeneration be larger than 1, meaning for every tritium atom you burn, you generate more than 1 tritium atom in the breeder. Lithium is abundant supply on Earth. You may not like where it's abundant, but in terms of actually being there as a resource, there's enough for it lasts for hundreds of thousands of years. The feature about that is these are not elements that are restricted to one particular country, that, for example, oil under Saudi Arabia or natural gas in the United States and in Tunisia, where their political implications control the fuel supply. Here for fusion, basically anybody can have access to that fuel resource. So what are the advantages of this as a power product? Well, for one, it says low carbon. It's actually no carbon in the fusion process itself. Of course, there may be carbon in how you put everything else together to get it into the system. The fuel supply is basically inexhaustible. It's deployable if you can generate electricity with it. It's complementary to all types of renewable energy. It's not necessarily in competition with them. What it does is it's very good for a baseload reactor. You want to run it like a nuclear fission reactor, keep it running for long periods of time, steady state, and then use that, the renewables, which are time dependent, to take the peak loading. It's intrinsically safe. So there are no nuclear waste products, there's no spent uranium, there's nothing long-lived products that you have to put in the earth for tens of thousands of years. The machine itself does get activated by the neutrons, so the material that's there at some point has a low level of radioactivity, but when you end of life of the device, when you take it apart, you can do shallow land burial for those, and in some 100 years or so, it's decayed enough that you can get right up on it. So there's not going to be a huge long-term problem with it. And the other really good feature is it's proliferation, nuclear proliferation proof. There are no fissile materials involved with this, so there's no danger of someone stealing part of the supply or somehow converting it into a weapon. And as Time magazine wrote, fusion is civilization scale energy, unlimited energy for everyone forever. We hope that's true, but we got to prove it. And I won't go into this because most people are aware and accept this, that time is running out to address climate change. So if fusion is going to contribute to allowing us to generate power without putting carbon in the atmosphere, then we have to get to it. Otherwise, we can't wait till 2050 or 2100 for fusion to come online. It'll be too late by then. We want to make a contribution before then. So how do you get the conditions for fusion? Well, you need enough fuel density, you need a fuel temperature, and you need energy confinement. The problem is these are very difficult to do. So let's talk about fuel temperature, for example. The temperature on the sun is about 10 million degrees C. For a fusion reaction to happen on Earth, because we do not have gravity to confine the fusion, we have to use magnetic fields. We have to get the temperature of the plasma much hotter than that. In this case, 100,000 C, 100 million C would be good. The other thing is you need enough density of the material so that these products are close enough together and there's enough interactions within a reasonable time period that you actually have time while you're heating it to get them to fuse together and give off energy. And so the other part of that was the confinement time. You need to keep them close, and you need to keep them close for a long period of time. For this is milliseconds to seconds time frame. Those things, this is density times temperature times confinement time. This is called a triple product, sometimes called a Lawson parameter, and this is a good measure of how effective your fusion process is. No one's ever made a machine that puts out more fusion power than has been used to generate it so far. They've reached the conditions for that with density independently from temperature and confinement times, but not all three together. So that's one of the goals. And nevertheless, people have always said, well, fusion's 30 years away and always will be. What you forget is there's actually been tremendous progress in fusion. So this is a performance indication. It's basically related to the triple product. And you want to get to a point up here. Above this point, you can generate, you can have what's called a capital Q of 1, where the fusion power is much greater than the energy you put in to sustain the reaction. So the goal is to get above Q of 1. When you get to a commercial machine, you maybe need to get to Q of 20. But the first part is to demonstrate that. Well, you can see the progress that's been made over the years. These are all different types of fusion devices. And when we got here to JET and to TFTR, we came within 0.65, so 65% of the way there. Of course, it's a log scale. But and that's performance increases faster than Moore's law for computer chips, and for our nuclear high-energy physics friends, it's faster than they've made progress with their high-energy accelerators. What's happened here is we're waiting for this device right now, which is called ITER, which will be the first machine to burn DT as planned. And it used to be proposed to be built here, and for many mostly political and funding decisions, it keeps getting pushed out later and later. So here they won't actually get to burning DT actually now in 2035. It keeps slipping. I'm going to talk a lot more about ITER, and you'll start to see why that's so hard. But this is not stagnation in physics progress or even in technology. It's stagnation, not saturation. I'm sorry, it's not saturation, it's stagnation. So here's JET, which is the Joint European Torus at Culham in England. It's the world's largest fusion device, and it's not superconducting. It's water-cooled copper magnets, and it takes a lot of pulse power and stored energy to make a device like this work. And if you really got good eyesight, you'll see that this is a drawing of it, and here's a photograph of it. And you look closely, you'll actually see there's a person here, and there's a person up here. So this is big, but ITER has to go bigger. This is inside the plasma chamber. It has to be very clean. You have to have 10 to the minus 8 torr vacuum in there to generate your plasma. And this is what a burning, not a burning, but a hot plasma looks like. Actually, you can't see the plasma, it's so hot, but what you do see is just the edges because they're cooler and they're radiating in the infrared region. And this region down here is called the diverter. This is actually where you pump out and exhaust the spent fusion products. So how does the device work? The most commonly used device and the most successful device is a tokamak. It's a Russian word. It was invented in Russia in the 1960s. Andrei Sakharov was one of the inventors of that. Some of you may know of him. But what's required are magnetic fields for confinement in some type of a toroidal donut shape. So I'll try to explain why you need these magnetic configurations. So if you have a magnetic field, just say from some solenoids, I create field lines. If I have a plasma, which is charged gas, where the ions and the electrons have been stripped, now I would get a rotation around those magnetic field lines at their ion cyclone frequency, which is proportional to their charge and their mass. And so if I just did a device like this, and there have been many linear devices tried, these particles will circulate around, but eventually they drift off. So the Russians said, and they'll go out the end unless you pinch the ends off, which is very hard to do. So the Russians basically turned it on itself and made a torus out of it like this. And so you can't lose particles out the end. They're always in there. However, they can still drift off radially. So the other feature of a tokamak is to induce a current in the plasma itself. The plasma is a charged gas, and by transformer action, if I put a big superconducting magnet, for example, or resistive for the smaller machines, and I pulse this like the primary of a transformer, then I can induce a current in the secondary, right in the plasma itself. And what that does is it creates what we call a poloidal field, its own cell field, and if I add those together with the field lines made by the TF coils, I get a helical pattern to the field lines. And that helps recycle the particles and keeps them in the region where you want them confined for much longer periods of time. The central solenoid in JET, that machine I showed you actually has iron return frame, but this is one of the there's only 2 machines that actually do that. Most machines just use air core solenoids. It's often called the central solenoid for obvious reasons, but it's the primary of the transformer. And what you do is you charge this up to very high magnetic fields. You have your gases in there that, in this case, if you were going to do a fusion burn, you do deuterium, tritium. And then you start discharging the magnet very quickly. That creates an electric field which breaks down the plasma, makes it start conducting, and it starts inducing current in the plasma. And you keep driving that bipolar to a negative very high magnetic field, and you can drive the current up to millions of amperes. In ITER, that plasma needs 15 million amperes going through it. So if you look at one of your wall plugs that carries a maximum around 15 amps, you have to induce 1,000,000 times more current in this. So we're talking big numbers when you get to fusion. The other thing is for this coil is because you're driving that current through the plasma itself has some resistivity of its own. That's heating the plasma from some of that coupling power. That's called ohmic heating. So sometimes that coil is called an ohmic heating coil. And then there's another set of colloidal coils that you see here called PF coils. And they're to shape the plasma, position it within the plasma chamber, and to stabilize it. So these are to make radial forces on the plasma, and you can stretch it, you can push it together like this, and you can make all different types of plasma shapes. The plasma heats, wants to expand, you can push it back in. It goes unstable, you can keep it in its position. So there's two sets of different functions for these coils. So the toroidal field coils are on DC all the time, and their problem is the heat load that may come to them from the fusion reaction itself, because they're closest to it. These coils are pulsed all the time, and that gives you AC losses. That was the reason I showed you that magnetization loop. So some of these are going through big closed hysteresis cycles, and that's an energy that you have to remove from those magnets. The tokamak is leading fusion performer. These are just some of the presently active systems. You can see it's basically in anywhere in the industrialized world, and in India now, and China, Korea, Japan. So the physics of it is fairly well established. What would we do with it? If we can make a reactor that gave out net energy, basically you would use those neutrons to heat a fluid, which you would then exchange with water to create steam and drive a turbine. So everything on this side is technology that exists. Everything on this side is the fusion power plant. So don't forget that, because people say this is expensive. But if you can get this, if you get down to a point where you can get a low cost of power generated, electrical power generated from this, this part of the plant still could be 50% or more of the overall plant cost, and is conventional technology. So let's look at some of these magnets for fusion, what they look like and how they work. First of all, there are some working large-scale superconducting fusion magnets worldwide. As a US citizen, I'm embarrassed to show you that there's nothing at all in the Western Hemisphere. But there's several working still right now. One of them is West, and I say ne tor supra because this was one of the earliest in Europe running reactors. It's been reconfigured, and it has a new name now. That's all superconducting. T7 and T15 are early tokamak reactors that were done in Russia, superconducting. Neither one of those is functioning right now. ITER is being built. I'm going to go into that. K-Star and EAST are running now. Trium was an old system that was not being run right now in Japan. LHD is a large helical device, and I'm going to talk about helical devices in a little bit. And JT60 is a new superconducting machine that's getting built, and India is building a superconducting tokamak 2. And Wendelstein is a very interesting device. It's called a stellarator, and I'll show you what that looks like. So here's Tor Supra. The coils are superconducting. Only the TF coils were superconducting on this. It used resistive colloidal coils, but you can see it's reconfigured plasma chamber. And as I mentioned, this is the other machine that uses iron for the return flux from the central solenoid. These are the other working fusion machines. So this is K-Star in Korea. This is EAST in China. This is the machine JT60 super upgrade that's being built. It's under construction now. It's a joint project between Europe and Japan, and it's a side project from the ITER project that had to do with an agreement between them when they had to choose a site for ITER between Europe and Japan. There was a big standoff for a couple of years, and everything was going to end until the Europeans offered to spend a lot of money to help them build their own smaller machine. So that's what that happened. And this is the large helical device in Japan. Helical devices look more like this. So in a tokamak, we had to make the spiral field, and in that case, we had to induce a current to do it. In a stellarator, or a helical device, you actually shape the magnetic field completely in a helical orientation just from the magnets itself. If you can do that, then you don't need this pulse magnet to induce the current, and all of a sudden it becomes a steady state device. And that's very good, as any engineer would tell you. It's better to be steady state than having to run a pulse system. The plasma physics in this looks very good. Some people think this may actually be the form that a fusion reactor would be eventually. It's just that the physics is not developed as much, and there's been very few machines. And one of the reasons there's been few machines is because they look something like this. So I like to call this is Wendelstein. It's a stellarator that's operating now. It's superconducting in Greifswald in Japan. It took a long time to build, and it looks like a tokamak that fell off the back of a truck. You may not, if you look closely, you'll see there's actually a 5-period repeating symmetry in these devices. And you can see, here's the machine being assembled, and you can see the complex shape of the magnets. They're all twisted and distorted. So this is a typical way that a plasma physicist solves the physics problems. They just put all the problems on the engineer to make something that's way too complicated and expensive to build. Nevertheless, from a physics standpoint, this is a very interesting device. So now I'll go to ITER, which is the big daddy of the tokamaks that's being built. And ITER is a tokamak that's been, let's say, studied since the late 1980s. There was a conceptual design phase, an engineering design phase, and now they're in the construction phase. When it first started out, it was just a collaboration between Europe, Japan, Russia, and the United States. So that was the way it was through the engineering design activity. After that, the U.S. dropped out for a while, and then China, Korea, and India joined, and the U.S. rejoined. So now there's 7 parties all involved in this project, all contributing to building it as contributions in kind. So let's look at it a little bit. So this, you can kind of see the tokamak in the cryostat here with the plasma inside. And again, I point out a person for scale. So now we're on a scale that's way beyond even what we saw for jet. So you can imagine how much cost and effort and time goes into building a machine like this. And these are all halls for radio frequency heating. You heat the plasma by radio waves. There's all types of hot cells if you have to change components and bring them out. So there's a very complex system to support and run and maintain a tokamak. The other thing is these components are big and very heavy. So there is one of the biggest lifts is the central solenoid. There's a crane up here that you don't see that can lift 1,000 tons. That's sort of the maximum load it has to lift. This is the site in France. It's about 50% complete. It's near Aix-en-Provence in the south of France, which is a beautiful region to go visit. So if you have an excuse to go visit ITER, then you can have a nice holiday while you're there. The machine is, as I said, many, many years behind schedule and way over budget. The cost, the official cost is something like $20 billion, but realistically it's probably costing $40 billion. The reasons for that are complex, but mostly political. It's the way the system was organized. There wasn't a central fund and a central team where the 7 parties just threw all their money in, and then they had the central team design something and then put out contracts to industry for the best and most economical products. Here, the machine is built, 80% of the cost of the machine is contributed by the 7 parties, meaning they give contributions in kind. So for example, for the toroidal field coils, there's 18 of them, and Japan is building 9, and Europe is building 10, actually, 9 plus 1 spare. So now you got to set up factories, and all the other components are split up like that as well, for the most part. So now you have multiple factories doing the same thing. It's not that efficient. You have to ship them from all over the world. You have to train different teams. You can quickly, and it's very hard to figure out how you're going to do the interface control and assembly and put all these things together when they're coming from thousands of miles away. So this is what the magnet system looks like. Here's the toroidal array. Here's the central solenoid. Here's the colloidal coils, as I showed you, so it's just like a standard configuration. Now, this is what they look like in real life. So that's a toroidal field coil. Actually, it's not the coil. It's the case for the coil, but this coil has actually been produced and is being shipped to Europe now. This would be what it looks like assembled. They use a conductor, a superconductor, that looks like this. It's called a cable and conduit conductor, and I'm happy to say this concept was actually invented by my predecessors at MIT in the 1970s and 80s. Basically, you make a big multi-strand cable in stages, in this case 5 different sub-cable stages with different twist pitches, and there's about 1,000 superconducting wires in here. And they're compacted in this conduit, which is actually a structural member, and there's about 30% void fraction in here, and you cool it by pumping supercritical helium through it. These are being made in lengths up to 1,000 meters. Now, that's a long ways for a cooling path, usually they're split into shorter segments than that. But that's another reason why you use supercritical helium, a single-phase gas, liquid, so you don't have to deal with vapor binding in the system. The scale is interesting too. This is 40 millimeters by 40 millimeters. This bundle is about 5 millimeters. This is a single superconducting niobium-3 tin wire. It has thousands of superconducting filaments in it, and this is what one superconducting filament looks like. This is a few microns in diameter. So just to make a wire like this is a very complex and expensive materials processing process. But good niobium titanium and good niobium tin wire is now made by companies all over the world. This is what the TF conductor would look like, and it's similar. It's round because it actually gets supported in radial plates in the coil. This is what the central solenoid looks like. It's made up of 7 modules. Here's one being fabricated at General Atomics in the US. This is a fixture for rotating it, and that goes in the core here, as you see. These are tie plates that are very hard to make to keep this thing together because of all the huge electromagnetic forces. And this is what the colloidal field coils, the bigger ones, look like. The biggest one is 24 meters in diameter. They're too big to ship, so they were actually built in one of the buildings adjacent to the tokamak hall on site, because it would have been too big to try to transport. Now, this is the path, the traditional path to fusion energy using the tokamak. So we have the machines up to jet size that are operating now. We have some superconducting machines like JT60, which is coming online. East and K-Star are in the same size and format as this. These are not designed to do DT fusion and to get to a gain of greater than 1. They're basically there to do plasma physics experiments and studies, learn how to shape and control and stabilize the plasma and all different types of processes that go on. ITER is the device that should actually do burning plasma. It should have a Q of 10 for 300 seconds and a Q of 5 for 1,000 seconds. Those are the main missions to show that you can generate and maintain a high power burning plasma for a long period of time. But you can see the time frame keeps shifting out here. It's up to 2030. Then in the US, they want to build what's called a fusion nuclear device, fusion nuclear science facility. And this is just to make a burning machine, but to put high neutron damage and heat loads onto all the material components that are in there to basically qualify it as the nuclear core of the machine. And then to make a net electricity generating commercial device, they want to go to demo, and you can see the demo scale is twice the scale of ITER. This looks a little bit too crazy. They're too big, they're too complex, they're too slow. But that's not the reason to abandon the tokamak. The concept is okay. So one way to look at this, and I apologize for the equations, but it's actually quite simple. So one is the how reactive the plasma is, and one is you have to confine them. So if I have a low magnetic field, I have big radii, gyro radii for the charged particles. If I increase the magnetic field, I reduce that radius. That means in the same volume, I can pack a lot more of these particles. And as I mentioned, you want to get to very high density. So you can see that you get a real gain by going to increased magnetic field here. The other issue is the plasma pressure. This plasma contains energy. It's like a balloon trying to burst, and you have to use the magnetic fields to confine it. If you want that to be a very high pressure and temperature, you need stronger and stronger magnetic fields. So the plasma physicists do everything by empirical correlations. They have data sets for basically every shot every tokamak has taken over the last 20, 30 years. So they have this incredible database of all kinds of scattered data for different performance parameters, but they put a linear line through it and they can get some scaling. So here's the triple product, and forget this, there's two features you see here that I want to point out. The triple product goes as the radius to the 1.3 power and the magnetic field cubed. And the power density, which basically is the economics, goes as the radius times b to the fourth. Now you can see why the machines are big. If you stick with niobium-3 tin, ITER, for example, the peak field at the TF coil is about 12 Tesla, and at the central solenoid is about 13 Tesla. And that's sort of the limit that you would maybe want to go through for a device that big. So to get enough power out of it, they increase the radius. And that's the reason for going to a bigger machine for demo. However, you look at this and you say, well, geez, why don't I just increase the magnetic field? Well, this is what happens if you increase the magnetic field. So this is the size of the machine in meters, and basically by size, it's the distance from the center line of the machine to the center of the plasma versus the magnetic field. And these lines are lines of constant gain, fusion gain. Remember, we want to get to a capital Q greater than 1. So you need to be out in this region somewhere. So you can either be big and low field or small and high field. So when you're using limited fields, this is the field at the plasma, this is ITER about 5.5 Tesla. It's 12 Tesla at the coil, but it falls off as 1 over R. So by the time you get to the center of this big plasma, it's only 5.5 Tesla there. You can see with niobium tin, you can't get into this range. And that's why ITER shows up right here. However, you want to be out in this range if you can, like on a Q of 20. And some students and professors at MIT came up with a conceptual design for a machine called ARC that said, look, what's the most compact machine we could make if we increase the magnetic field to make it practical, to get down into a size like this, and they call that design ARC. And you can see that the field at the plasma goes from 5.3 Tesla to 9 Tesla. That's almost a factor of 2. A factor of 2 times b to the fourth is a factor of 16. So it's a huge multiplier, and that's what drives the size of the machine down. Now, of course, that's a very big step to go to a burning plasma at that size because it's going to put out a few hundred megawatts, well, 500 megawatts of fusion power, a couple hundred megawatts of net electricity. So what you want to do is make a smaller machine, but as high a field machine as you can to keep it small. And that's a device that the people at MIT and now a company called Commonwealth Fusion Systems called Spark. And that's to be out in this range. Q's greater than 1, with between 1 and 10 typically, but a very high magnetic field at the plasma. basically going to 3 or 4 times the field of the ITER device. And what allows us to do that is the game changer, which is high temperature superconductivity, allows us to go to that. Now, I apologize for this being complex, but this is the critical current density at 4.2 Kelvin versus magnetic field for all types of wires. So niobium titanium, the low temperature superconductors are in here, niobium 3 tins in here, and you can see how it falls off by 20 some Tesla. You can't go higher than that. Of course, for design reasons, you always operate at a field lower than that. But you can see these new high temperature superconductors have lines coming down like this. And you can see they extend way out with very low slopes into very high magnetic fields. So what makes it a game changer is to go to high fields, so you get these gains. The magnet gains in stability if you can go to higher temperatures, operating temperatures as well, because the heat capacity of all the materials gets bigger, and you can put more dissipative power into it and absorb it without crossing the critical temperature. The cost goes down, presumably by decreasing the machine size and volume. This is a long-range goal, is because these, if you operate them at 20 Kelvin or above, as opposed to 4 Kelvin, then you can sustain a resistive heat load if you can make resistive joints, demountable joints. There's a gain there for maintaining the machine because it will allow you to pull it apart later. I won't go into that, but that's a major issue. And you can basically use it for any magnetic configuration. Here's a plot of the current density versus applied magnetic field. And you can see this is the LTS. This is where ITER is operating. The high energy physics people are looking at a future circular collider where they want to be out at 16 Tesla out in this region and maybe up in here. But still, when you compare it to a HTS range, you can see the type of space it gives you to operate in. And again, this is looking at field versus temperature. You can do it high field even at high temperature. So these are two tremendous features that say, let's go with HTS. But it's a complex and expensive material, so here's how an IPCO tape is made. It's basically made on a reel-to-reel system, and it's a coated conductor process, and it's very complex. So you would start with a hastelloy substrate, for example, and then you build up what are called buffer layers, and then you lay down a superconducting layer of the IPCO, and you put a small layer of silver over it for the reaction heat treatment, and then maybe some plating of copper. In dimensions, this is about 0.5 millimeter. These are nanometers. The superconducting layer is 1 micron. So when you have a tape in front of you, the whole thing is maybe 0.1 millimeter thick and 4 millimeters wide is a typical one you would buy. And maybe it can carry hundreds of amperes at liquid nitrogen temperature, maybe 1,000 amperes at 4 degrees Kelvin, and then again, depending on the field, it goes down. However, that current, that supercurrent, is carried in this 1 micron thick layer. It's phenomenal. There's hardly any material in there. But it's very hard to make and process and get the grains aligned to be able to carry a lot of current. Here's another form. Again, there are different manufacturers with different processes. These are the companies that are making this now. I probably missed a few, but there's about 12 or 14 of these I think I have up here. So there's 4 in the United States, there's 4 in Germany, there's Korea, Japan, China. Actually, I think there's a second one coming on and one in Russia. So they all have their own processes, and this is good for the field because there's a lot of competition now to see who can make the best wire product and make the most of it. To show that you can actually operate a HTS high magnetic field, several have been built at extremely high fields. So at Tallahassee, Florida, the National High Magnetic Field Lab, they built a 32 Tesla all superconducting magnet. They have a background coil made from a commercial company using low temperature superconductor that goes to 16 Tesla, and then they make another 16 Tesla from this little coil right here. And that machine is now being commissioned. Of course, these are small bore devices. This is an all IPCO, in this case gadolinium. That's why they're called REBCO sometimes, because you can replace the yttrium with other rare earth element, in this case gadolinium. This is made up of a bunch of pancakes of this type of conductor. This thing itself went cell field to 26 Tesla and 35 millimeter bore. So the material works. The question is, can you do the engineering to get the device to do what you want? At MIT, we developed this, what we're calling the twisted stack high current conductor. You need high currents because you have very big devices. You want to keep the inductance low. You don't want to have to wind so many turns. So we want to develop conductors that can carry maybe 50 to 100 kiloamps. And you do that, in this case, by stacking tapes, putting them into copper in some configuration, and then assembling them and bundling them up to get to as large a sizes as you need to go. So this is still, fairly research stage. And because of the high fields, to test their limits, it's very difficult to even find out if these work without having to build a full-size magnet. These are some other configurations to show that you can get up to over 100 kiloamps here. And there are other countries working on it in national labs. So in Germany, there's the Robel, which was invented at Karlsruhe Institute of Technology, but actually is put together here now on a more commercial basis at at Robinson Research Institute. Here's some twisted stack tapes at MIT. This is from a fusion laboratory near Rome in Italy. This is a USA concept and a commercial company. CERN is starting to look at this for their future circular colliders. This is a Switzerland concept and the Japanese concept. So there's interest in this all over the world. These issues are all funded still by government labs. However, in recent years, there's been a new paradigm for fusion energy, and that's many startup companies have formed to accelerate the path to commercial fusion energy. What's interesting is there's no government funding. They're all funded by private investors and industry, because they see the need for fusion, putting power on the grid, and they actually think, particularly with the development of high-temperature superconductors, that there's a path to get to a more reasonable device. And there are multiple devices and multiple paths that these companies are taking, but I didn't realize there were even this many, but there's now a Fusion Industry Association, and there's something like 24 names on here. They're not all fusion companies, but at least more than half of them are. And they all have most of them have different concepts. I'm going to talk about these two, Tokamak Energy and Commonwealth Fusion Systems, because these are the ones that are concentrating on the tokamak path. So these two funded companies, Tokamak Energy is in Oxfordshire, UK. It's basically a spin out of people from the Culham laboratory, where they have this big fusion machine jet. And they're developing a device which they call a spherical tokamak. Spherical tokamak is basically a tokamak with an exotic shape to it. And then Commonwealth Fusion Systems in Cambridge, which is spun out of MIT, and they're developing a machine called Spark. This is what Tokamak Energy's first net fusion burning machine would look like. That's sort of the scale. And they would use high-temperature superconductor based on REBCO. They've raised 50 million pounds from private investors. They continue to look for more. And their goal is to generate fusion energy by 2030. This shows a photo not of this particular machine, because this isn't built yet. This is going to come way out in this time frame. This is another spherical tokamak. It's a resistive copper machine that's running at Culham now, next to the jet facility. It's called MAST. And you can see this has a very different aspect ratio than the sort of elongated plasmas. There are some physics reasons for that they believe is going to make a better machine, but the physics have not yet been completely demonstrated on that. This is what the Spark machine would look like in concept. Again, it's of a similar small scale. The Commonwealth Fusion Systems, they've had a first round of private financing. They collected $115 million for the first phase, all from private investors and a few large companies. ENEL, which is a Italian oil and gas company, actually put in the first 50 million. And then there's money coming from some rich billionaires as individuals, and also from Breakthrough Energy Ventures, which is a consortium of, again, some Bill Gates and Jeff Bezos and other billionaires have put their money together to look for some special projects that they want to do make a difference with global warming. The first goal is to demonstrate a large bore, high field magnet, something of the scale of one of these, in 3 years using the Rebco technology. And if successful, then they'll build the machine, which will be sort of a 100 megawatt net energy device, and do it in 4 years. The device would have a field at the bore of 12 Tesla, which means it's over 20 Tesla at the coils. So it's a huge engineering challenge for the magnet designer, because the stresses go as the square of the magnetic field. So it becomes really more of a structural mechanical engineering issue in many ways than a superconductor issue. And their development path is to start with a high temperature superconductor, but multi-tape high current cable. They're at this stage where they've already developed this, and now they're designing, and they have about 2 more years to design and put together and test this. This is the major milestone. If they test this, then they go to the second round of funding, where presumably they collect another $500 million, and they actually go ahead and build this device in another 4 years. That would be incredible if you could do it. It's going to take a lot of HTS tape, which is very expensive. So a big chunk of that money is going to buy tape. They have orders out now for $15 million worth of tape. And you can see that they're up to this stage now where they're buying 50,000 kiloamp meters for this TF model coil. That's a huge number. And then they have to go 18 times more than that to actually go to the phase 2, where they actually build the entire machine. They have at least 3 vendors at different companies around the world that are making tape that very well meet the spec, and they're trying to scale up to production to meet the quantity and on a time scale. This is very important for the applied superconductivity industry, because this is sort of the breakthrough that people need to start to force the cost down of these devices and improve its performance, because there's now money behind it, there's orders behind it, and people can start investing in scaling up the production rates. And that's one of the goals of this project as well. And then the step after Spark would be the ARC machine, which I mentioned earlier. And you can see it to be similar to ITER, but a lot smaller. Here's the human for scale. And also to come online much sooner. So that development path, which we call the fast track, this is JET. This is ITER, and that would be demo way out here in 2060. And as I say, that's way too late. This is Spark, is supposed to happen around 2023, 24, and then by 2030 to 35, you'd have ARC, which would supposedly be the net machine that puts net electricity on the grid, the first real prototype power plant. So that's the goal of these devices and the fast track. In summary, I just want to say that the low temperature superconductor technology is very well advanced and developed for fusion applications and for many other applications, both niobium titanium and niobium tin. But if you need to go to fields higher than that, then you would like to look at high temperature superconductors, and particularly to get to the scale of ITER and devices beyond that, you would want to definitely go to a high temperature superconductor. And as I say, there are other practical large scale applications that will spin off from this as well, as a lot of that work is being done here already at Robinson Research Institute. Thank you. I forgot to mention that, because I changed my talk and the slides fell out, there's a lot of work going on in New Zealand here. So I mentioned Robinson Research Institute. They built a device for characterizing the superconducting tape as a function of field and temperature and angle of the field with respect to the tape. It's a very beautiful automated system. Originally, it's an 8 Tesla system, and guys from MIT have come here and from CFS and characterized a lot of tape with it. And now with HTS 110, they've built a higher field machine, which they're just delivering or ordering to MIT to go to 12 Tesla, so they can start getting a good database on the materials they're going to be purchasing. The other thing that Robinson Research Institute is doing is they put that information, the data that they take from measuring the superconductors, into a database, which is a public database. So they have data from tapes that they've measured from coming off all different manufacturers from all over the world. And that's very good for researchers to be able to go to that and look at the scalings with temperature, field, and use that for design purposes and analytical purposes. And then there's the other company, Cirrus, which is doing 2 things. One is for ITER, actually, because they're doing a special type of materials to put tungsten onto steel as backing plates for the plasma-facing components, which are these high power and high heat flux devices that have to look at this 100 million degrees C plasma. So you need good conductivity and you need good damage protection. And so they're looking at a special metallic process in order to do that and put these tiles on the inside of the device. And the other one is they're working with one of those HTS companies, STI, to improve their materials processing as well.
Right. Thanks very much, Joe. We'll take a couple of quick questions, and there's also time to ask Joe questions later. We're having some light refreshments in the mezzanine floor, which you can go out here and up the stairs or out the back of the lecture theatre. So we'll just do a couple of quick questions now. And Tane will run up and give you the microphone.
Thanks a lot for that. You're Carl Upson here. Just wondering, a couple of quick questions. Maintenance-wise, what's the likely lifespan on, say, RIBCO superconductor materials and on the reactor core materials?
It's a good question, because no one has long-term experience with it. One thing that people are trying to do is cycle them electromagnetically, to make sure that they stay together, that they don't delaminate with, because they have huge Lorentz forces generated in them, carrying kiloamps and 20 Tesla magnetic field. So there's studies going on for the mechanical properties of the device, both static and under strain. The decay or some type of chemical degradation is not likely to happen if you maintain them most of their life at cryogenic temperatures, but there's really no decades of experience. I will say most superconducting magnets, if they're designed right, you energize them the first time and they're good for decades. I mean, there are some magnets that have been running consistently for more than 10 years and so on. So particularly if it's a DC device. So, but that depends on getting good engineering design. If you have a bad design, you probably catch it when you first turn it on, because you may damage it, break it, or something like that. But once you get it up to performance, usually they stay there.
Final question here.
He's getting his exercise today.
I actually know very little about science. The only time I heard about fusion a long time ago was in 007's movie. But anyway, I was wondering, when you talk about, because it's political, a lot of political reason, and why government doesn't invest in such an important area, I guess maybe they didn't think the science is mature yet technology is mature yet and a cost-effective reason. Say if in an ideal world, we put all the world military budget and defense budget and, you know, come invest in this area. I know it's bad for me to ask this, but how much the certainty for the academic or scientists have to say, well, we can semi-guarantee or guarantee a certain progress, say we can actually really save the planet if you throw the money in?
Okay.
Just a very superficial question.
That's a good question, and since you mentioned politics, I'll put in a political comment. And I speak principally from someone living in the United States. Is the U.S. has more than enough money to put investment to build a device, these types of devices, and put it on a fast track by putting more money into it, more research effort into it, and actually construction effort into it. It's just how people choose to spend their money. But there's no guarantees. I would think people are pretty well convinced, scientists are pretty well convinced, if they can build a machine like ITER or get to that, or now the people at CFS and MIT use the same physics scaling as ITER, so if everybody thinks ITER is going to work, it's likely that this machine will work, as long as you can build it and maintain it. That's not a guarantee that it's going to be an economical or commercial device, because as you can see, they're big and they're complex. Even the compact ones are very complex. There are many systems in there. And so it's not like a fission reactor, which has very small number of components, and most of them are not moving or active or pulsed. So there's a lot of work to do to show that you can build these, generate electricity on a profitable economic basis, because you also have to keep them running for very long periods of time. You need to, they call it the uptime. You know, they need to be running 90% of the time. You can't, like an experimental device, when something goes wrong or wears out, you shut it down and take it apart. So that's a long road to go to show that you can proliferate them. But that's a reason to go to the more compact device, because you can build them and test them, turn them around earlier and change your designs so you can innovate much faster on that, as opposed to a 20-year time scale like ITER.
Okay, thank you very much, Joe.